In 3.02, we're going to continue talking about electricity. We're going to do the electric current in 3.02. So now we've learned about conductors and insulators, that metals are really great at conducting electricity. And this is because the atoms in metal have a very loose hold on electrons. Further from the nucleus, and this allows electrons to move freely about from atom to atom when they then experience the electrical force. So the flow of electrons through a solid metal is like an electric current, where it just continually flows through it. The electrons that make up the electric current are already present in the metal atoms. They just need something to get them moving. So see how the outer electrons of these metal atoms are able to flow from one atom to another when they experience electrical force? See that when they have the positive, they flow from negative to positive. So the lower affinity here to the higher affinity in the positive. They always go from lower to higher, or from negative to positive. So to see how it really happened, we would have to do this at speed it up more than 1,000,000 times to see what really would happen in real life. But we slow it down so you all could see how it flows without having to miss it. So electric charges. When they have a charge, we know there's an imbalance, the number of positive protons and negative electrons. We talked about that last time. We have a +1 or a -1, and that's an ion. Okay, we know electric charges can develop in atoms where they either gain or lose electrons. This movement is called electric current. You see it jumping over? Now this one is +1 and this one is -1 because the electron, which is negative, went from here, making the positive protons have more than the negative electrons, and jumping over here makes it have more negative electrons than positive protons. This one have a -1 charge. We can also categorize how quickly or rapidly the electrons can flow from one to the next, and which is the rate of movement of charge, and also the force behind electron flow, and that is the electromotive force. So the rate at which they flow is called amperage. We can liken this, or this is similar to the rate of flow of water in a river. Just as a river has a current that can be expressed as volume of water passing through a certain point per unit time, so can electric current be expressed as the amount of charge passed through a certain point per unit of time. And this is called amperage. So we'll have to kind of figure out what these units are. And one unit is a coulomb, and this is the amount of electric charge transported in 1 second by a steady current of 1 ampere. Electric current is the rate of flow of electrons. Electric current can be defined in terms of coulombs per second, and then we have 1 ampere, or amp, is defined as the rate of charge flow equal to 1 coulomb per second. Okay, we're going to drag the light bulb over to the socket and turn this switch and observe what happens to the ammeter, which is right here. So we're going to put the light bulb in the socket, watch the ammeter. Okay, what happened there? What'd you notice? That the ammeter went from low to high when we have the light bulb plugged in and it is turned on. So what does that tell you about the flow of electric current? What does that tell you? It goes from the negative and flows to the positive. And that the electric current is able to flow when we flip the switch. So the switch completely controls when the electrons can flow through. Okay, voltage is similar to water in a dammed reservoir. The water is kind of like the electrons that are flowing through. A small dam wouldn't provide a lot of water pressure behind the river's flow, but a large dam, the large reservoir of water, provides a huge potential pressure behind a river's flow. And this is what voltage is similar to, and it represents the amount of pressure behind the electron flow. Instead of gravity being the force as it is in the river, electric charge is the force behind voltage. In either case, when we have the larger difference in the charge between the two locations, the larger the voltage will be. Bigger voltage, bigger pressure for electrons to move between two locations. So let's look at the animation. So we have electric fences, and they're often labeled with warning, it has a certain amount of voltage and amperage. Human and animal bodies can both act as really great conductors. If you've ever gotten close to a radio, you notice the closer you get, the better the quality, and the farther away, the more static it gets, because your body's conducting electricity near that radio. When you have high voltage and high amperage fences, that results in greater damage to both human and animal, rather than opposed to a low amperage fence. You may have high voltage in both fences, but low amperage fence would involve a lower rate of flow of electric charge. The amount of electric charge experienced by the animal is much less in this case. So high voltage, low amperage, high voltage, and high amperage. Let's find out what happens. So he's getting a much larger amount of shock because of the high amp as well as the high volt. They both have the same amount of volts, but one has a higher amperage, means the electrons are flowing more rapidly. So the force behind the water faucet is the same no matter how you adjust the handle of the faucet. This represents the voltage. When the faucet handle is in the off position, there's no water. The water pressure is there behind the faucet, but until the handle releases it, it's going to stay there. So this is 0 amperage. When you turn the faucet on a small amount, a small flow of water comes out of the tap. Again, the water pressure has not changed, so the voltage remains constant. However, the rate of flow is low, so this represents or resembles low amperage. The farther you turn the handle, the greater the volume of water that flows out in a particular time. That'd be the amperage. The voltage is still the same. The pressure is all still there. It's all waiting to be released. But the amperage just lets you determine how much water is released. So the power is volts times amps, so that's V times I equals P. Now you can understand why the cow in the previous got a much larger shock when the amperage was higher, because there's more electron or more electric charge being released. So we talked about that previously, that power is voltage times amperage. And we also talked previously that power is the rate of doing work. It describes the rate of energy transfer from one object to another. In this case, we're talking about electrical power. In Module 1, we talked about how much force is being applied over a certain amount of time. So it's still the rate of energy and transfer from one object to another, just one is electricity and one is just work. Power is often measured in watts. The electric company also measures your power usage in watts and the amount of time you use those watts to determine your electric bill. Explore the amounts of power, which is the rate of energy use and total energy used in an average household under different conditions. In the following interactive, begin by choosing American house that runs 120 volts per 60 hertz hour. So you're going to do the assignment for 3.02, and I look forward to talking with you in 303.